Last time, we stacked neurons into a layer and watched a flat sheet of space bend into a curve, just enough to separate points a single straight line never could. And I left you with a warning. That curve only exists because of one tiny kink we kept glossing over. So watch what happens when I reach in, grab that kink, and pull it out. The curve goes slack, it flattens. And every point that was neatly separated a second ago collapses back onto one useless straight line. That tiny kink has a name. It is called an activation function, and by the end of this video you will understand exactly why it is the single most load-bearing wall in all of modern AI. Here is the promise. You will see, with your own eyes, a tower of 100 so-called deep layers algebraically collapse into one. You will see why the simplest, dumbest function imaginable is the thing that woke the whole field up. And you will leave knowing the one rule that separates a network that can learn anything from one that can only ever draw a line. Let's go back to a single neuron, because it does exactly two things. First, it takes all of its inputs, multiplies each by a weight, and adds them up, with a bias on top. That weighted sum is the vote. We have spent 2 whole episodes on that part. Then it does one more thing we have always skipped. It passes that vote through a function we'll call f, the activation. If the weighted sum is the vote, the activation is the decision. Today is entirely about f. Now, why does f matter so much? Start with what one layer can do all on its own with no kink at all. A single layer just computes weights times input plus a bias. Geometrically, that is a straight line, or in higher dimensions, a flat plane. It can only ever make one straight cut. Remember the XOR points from last episode, the ones arranged so no single line can split them? A bare linear layer stares at them and fails. One line. That is the entire menu. So you do the obvious thing. If one line is not enough, stack more layers. Make it deep. Surely 2 layers can do more than 1, and 100 layers far more than 2. The whole field is literally named after this idea, deep learning. More depth, more power. It feels so obviously true that almost nobody stops to check it. So, let's check it. Let's actually do the algebra, slowly, and see what stacking really buys you. 2 layers, no kink yet. The first layer takes the input and produces a hidden result, call it H. So H is the first weight matrix times the input, plus the first bias. The second layer takes that H and does the same thing again, its own weight matrix times H, plus its own bias. 2 genuinely separate steps, 2 sets of weights, stacked one on top of the other. This should be strictly more powerful than 1. Watch carefully, because here is where the magic is supposed to be. Substitute the first layer into the second. Now, multiply it out. The second matrix slides through and meets the first, and 2 matrices multiplied together are just one new matrix. Call it W star. The biases fold together into one new bias. Call it B star. And look at what is left on screen. W star times the input plus B star. That is a single weighted sum plus a bias. That is one layer. The 2 layers just collapsed into one. And this does not stop at 2. Stack a third layer, it merges in 2. Stack 10, stack 100, and the exact same thing happens every single time. The whole towering stack telescopes down floor by floor into one flat box. 100 layers of so-called deep learning, with the kink removed, are mathematically identical to a single straight line. 2 layers, 1 line. 100 layers, still 1 line. Without the kink, depth buys you literally nothing. So now put the kink back and watch the collapse break. We insert the activation F between the 2 layers, so the second layer no longer sees the raw hidden result. It sees F of it. Run the exact same trick. The second matrix tries to slide leftward and merge, like it did a moment ago. But this time it hits the F and it bounces off. It cannot get through. There is no way to pull a matrix out through that function. The 2 layers stay genuinely, permanently distinct. Now this is the part that trips everyone up, so go slow with me. Why can the matrices merge but F cannot be absorbed the same way? Give me 60 seconds and it will click. Here is the intuition. Multiplying and adding, the only things a linear layer does, can stretch space, rotate it, and slide it around. But every one of those moves keeps straight lines straight. Do 1,000 of them in a row and you have still only done one big stretch and slide. A flat sheet, moved to a new place, is still a flat sheet. A nonlinearity is different. A nonlinearity is a fold. Picture a flat sheet of paper. You can slide it, spin it, stretch it as much as you like, and it stays flat. But the moment you fold it, you make a crease. And here is the key. No amount of sliding or stretching afterward can ever pretend that crease was not there. Fold is a one-way door. That is exactly why the matrix bounces off F. The kink already bent the space, and linear algebra simply cannot unbend it. And once you can fold, look at what you can build. You already met this exact move last episode. The most common kink is the one we folded paper with last time, ReLU. Positive, leave it alone. Negative, make it 0. One single hinge. You watched one hinge become a bump, and a row of hinges trace out a curve. I am not going to reprove all of that. I am replaying it for one reason, because there is a single property of this hinge we quietly glossed over last time, and today it is the whole story. Its slope. Here is the one breath replay since you earned this last time. One hinge, a single bend, a handful of hinges, a bump, 20 hinges, and the jagged line hugs a smooth curve. That is the picture behind the universal approximation theorem we met last episode, folds stacked up, imitating any curve. Old news. Now watch the new thing. Strip the kinks back out, and all of that power flattens into nothing. So everything hangs on the kink staying in, which means everything hangs on which kink we choose to put in. And remember the honest asterisk from last time. Can approximate is not the same as will learn easily. The kink only unlocks the possibility of a shape. The slow, patient downhill walk from the earlier episodes is still what has to go and find it. The activation opens the door. Gradient descent still has to walk through. So hold that word, learn, because the choice of kink does not just decide which shapes are possible. It secretly decides whether the network can ever learn them at all. So everything now turns on a single question. Which kink do we pick? Historically, there were 3 big contenders, and the choice between them is not a detail. It quietly decided whether deep learning worked at all for decades. Meet the lineup. Sigmoid, a smooth S-curve that squashes everything into the range 0 to 1. Then tanh, its cousin, squashing into -1 to 1. And ReLU, the simple bent line we just met. They all add a kink. They are not all created equal, and to see why, we have to look underneath each one at its slope. Here is why the slope is the thing that matters. Remember the learning loop from episode 0. The network makes a guess, measures how wrong it is, and then sends that error backward to assign blame, multiplying a chain of slopes together as it goes. That backward signal is how every layer learns what to fix. So, if a layer's activation has a tiny slope, it shrinks the signal passing through it. And if it has a healthy slope, the signal passes through clean. The slope of the kink decides whether learning survives the trip back. So look at sigmoid's slope, drawn underneath it. At its very best, right in the middle, its slope tops out at 1/4. And out at the edges, where the curve goes flat, the slope falls to almost nothing. The function saturates. It is like a volume knob that stops responding once you turn it past a point, and tanh is a little better. Its slope can reach a full 1 in the middle, but it too goes flat and dead at the edges. Both of them choke the learning signal. Now ReLU. Its slope is the most boring graph you will ever see, and that is exactly the point. On the positive side, the slope is precisely 1, not 1/4, not nearly 1, exactly 1. On the negative side, it's 0. No gentle saturation, no fading out, no choking. Wherever a ReLU neuron is switched on, it passes the learning signal backward completely untouched. Hold that number, a clean slope of 1, because in about a minute it is going to explain a 40-year-long failure. Here is the failure. Picture the error signal flowing backward down a deep tower built from sigmoids. At the first layer back, it gets multiplied by at most 1/4. At the next, at most 1/4 again, and again, and again, and again, layer after layer. Remember from episode 0, the chain rule just multiplies these slopes together. So multiply a long chain of numbers, each no bigger than 1/4, and the result does not shrink, it plummets. By the time the signal reaches the early layers, it is a whisper, then nothing. Let me make it concrete with the smallest possible case. Just 2 sigmoid layers. 1/4 times 1/4 is 1/16. The blame signal is already cut to 1/16 of its strength after only 2 floors. Now imagine 10 floors. You are multiplying 1/4 by itself 10 times, and the number you get is so small it may as well be 0, less than a millionth. The early layers receive essentially no signal at all. They never find out what they did wrong. This has a name, the vanishing gradient. And here is what that actually feels like for the network, using the picture we've leaned on all season. Learning is a ball rolling downhill on a landscape of error, always feeling for the slope under its feet. But when the gradient vanishes, the ground beneath those early layers goes perfectly, dead flat. A ball on a flat floor has no idea which way is downhill. It just sits there. The deepest, most important layers of the network simply stop learning. The network goes deaf to its own mistakes. Now, swap every sigmoid for ReLU and run the exact same backward trip. At each active layer, the slope is 1. And here is the beautiful part. Multiply by 1, then by 1, then by 1, as many times as you like, and the signal does not shrink at all. It arrives at the very first layer just as strong as it left. The error survives the entire journey home. That single change, a slope of 1 instead of a quarter, is the difference between a network that learns and a network that is deaf. This is not a story. This is the actual hinge that history turned on. In 2012, a network called AlexNet entered an image recognition contest and crushed it, kicking off the entire deep learning boom you are living in. One of its key tricks was almost laughably small. They swapped the fancy smooth activation for plain ReLU, and the network reached a given training error around 6 times faster. The dumbest function in the lineup, if it's negative, make it 0, is the one that woke AI up. Sit with how strange that is for a second. The smooth, sophisticated functions, Sigmoid and tanh, are the ones that broke deep networks for years. And the fix was the simplest line with a corner you could draw. Even better, ReLU is technically just 2 straight lines meeting at a point. People look at that and ask, how is that nonlinear? And the answer is the whole episode. You do not need a curve, you only need one kink. That single corner is enough to fold space into anything. But I promise honesty, so here is the catch even on the hero. ReLU has its own failure mode, and it's permanent. Remember, on the negative side, its slope is exactly 0. So if a neuron gets pushed into always outputting negative, it outputs 0, and its slope is 0, which means no learning signal ever reaches it again. It can never climb back. It is dead weight forever. They call it the dying ReLU, and it is why modern models reach for smoother cousins, like the one called GELU, that keep a faint slope alive on the negative side. And this is where today quietly touches the destination of the whole series. That smoother cousin, GELU, a softened ReLU, is the exact kink sitting inside the feed-forward layers of GPT-2, GPT-3, and the language models that grew into ChatGPT. The very newest frontier models use close relatives of it. So when you talk to one of these systems, somewhere in there, billions of times a second, a number runs into a tiny bent function that asks roughly, keep this, or push it towards 0. The kink from this episode is running, right now, inside the most powerful AI on Earth. So let's close the loop I opened at the start. The one rule. A neural network is a weighted sum plus a kink, repeated. Take the kink out, and any number of layers collapses into a single straight line, exactly the flat curve from the cold open. Put one back, and the layers stay alive and can fold space into any shape. And the slope of that kink decides whether learning survives a deep network at all. A clean slope of 1 is what finally let networks go truly deep. That is the load-bearing wall. But step back and notice something we have quietly taken for granted this entire time. Every single thing flowing into these neurons has been a number. The weighted sum, the kink, the downhill walk, all of it assumes the input is already numbers. Which raises a question we have dodged for 3 episodes. When you type a word, plain text, into one of these models, there are no numbers. So, how on earth does the letters of catch become a vector the network can multiply? The answer turns words into points in space, where meaning becomes direction. And that is next.